that it's going to be like review for a good number of you. I'll still teach it as much as possible, but I'll just be fast because it just deals with chemistry. Now, when I say chemistry, don't fret. Don't think like, oh, chemistry and panic. No, no. It's not that kind of chemistry. It's a kind of chemistry that you like. All right. I in a way to joke about it, I tell my students it's chemical biology. All right. Or it's biology kind of chemistry. So it's something that will interest you. And I mean it. Don't fret and be like, oh, I don't like chemistry. Don't freak out. It's a small chemistry that naturally you will get it easily here, and not the kind of chemistry that you will struggle with. Okay. Now, so this chapter deals with chemistry of microbiology. Now, the truth is this: there's some basic level of chemistry that you cannot do without when you talk about biology or when you talk about microbiology. Now, and that's it here. If you look at this, why do we talk about chemistry in biology or in microbiology? It's because as we study, we understand that the organization of life is traceable to atoms, which are the things that we talk about, and we call it chemical level of organization. So in the natural science, atoms give rise to molecules. And I'm doing this just to introduce it. Molecules give rise to macromolecules. Macromolecules give rise to organelles. Of course, many of you will be able to relate with these now. Organelles give rise to cells. Cells give rise to tissues. Tissues give rise to organs. Hi, baby. Organs give rise to system. System give rise to organism. You can see the board, right?
Yes.
All right, thank you. And organism give rise to, in actual sense, for this level, organism is it, right? But group of organism will give rise to population. Group of population, more than one type of organism, community. Then you have the ecosystem, which is the combination of living and non-living components. And then we have the biosphere, which is anywhere that sustains life. All right. So when you talk about atoms, then you're going to have to talk about the particles that make up an atom. The particles that make up an atom, it is there we have to talk about. We talk about, okay, I can write now, proton. You talk about electrons. You talk about neutrons there. So we call these subatomic particles, these three. We call them subatomic particles. The proton is positively charged, electron is negatively charged, and the neutron is neutral. All right. Now, what is matter? As you are sitting there, you are a matter. Why do I say you are a matter? Of course, you have mass and you occupy space. So since you occupy space and you have mass, you are a matter. This is a matter. It has mass and occupies space. All right. Let's go. Now, molecules. Okay, let me just give a little hint about this. So when you talk about atoms, you're talking about hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluoride, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Those are the first 20 elements, right? Those are atoms. When you talk about molecules, it's that you are combining the elements together. So, Diomedes, don't worry. I'm recording it so you can look at it again. Then when you look at molecules, here we say that oxygen is here. All right, oxygen is an example. Here, an example will be O2. What's the difference? This is oxygen molecule. This is oxygen atom. You don't breathe in the atom. You breathe in the molecule, which is the gas. All right. Here, you're going to have CO2 here. You're going to have H2O here. Oh yeah, I'm going to record it. I'm recording this so you have it. All right. You'll be able to listen to it again. And if you have any question about it, let me know, Florence. Don't mind me. My baby just saw me coming in, and she's trying to greet in and again. So macromolecules, we have protein here. All right. Macromolecules simply means larger molecules, right? We have carbohydrate here. Here you have DNA. You have RNA here. Those are macromolecules. Lipid is here. Lipid is here. All right. And we'll discuss some of them there. Now, for some of them, if we are able to discuss them fully, good, we will. If not, I have a lecture video that could be a refresher that I recorded for Bio 1306 or AP1. I can link that with you as well. All right. Then organelles, of course, you have, for organelles, you have mitochondria. Those are organelles. You have Golgi apparatus. You have endoplasmic reticulum. Those are organelles. You have ribosome. You have lysosome, organelles. For cells, of course, you have the red blood cells. You have white blood cells. You have, you say, neuron. Those are cells. You have muscle cells, which we call myocytes. Muscle cells. Muscle will be cells. So those are cells. Okay, those are cells. Sorry, my C is not written. My health. Don't mind my way I wrote it. It's muscle is MUSCLE, just in case you are not seeing it well. You have muscle cells. You have osteocytes. These are bone cells. Osteocytes are bone cells. You have chondrocytes, which are cartilage cells. All right. Leukocytes, the kind of white blood cell, monocytes, all of those blood cells. Now for tissues, I call it semen. I know there are some of my students here from AP1. You should know this already. Semen, this is connective tissues. I'm just giving you like a general view. Like I said, this chapter is, we have muscle tissue, we have epithelium, and then you have the nervous tissues. And I say, don't be nervous. Then organs, of course, organs, you have your heart, you have your lungs, you have your kidney, you have your eyes. You are going to give me 1 minute. Let me just say hi to this baby. She's been crying to say hi to me. Just give me a minute. Thank you. All right. I'm sorry about that. Okay, so those are organs. You think about the liver. Okay, so you think about the liver, stomach, pancreas. Those are organs. Then when you come to systems, do I have enough space here? There's this thing I have for systems. My AP1 student knows that already. Some of them that are here. I call system red monks film. I just use it as an acronym for us to remember system. So the R is respiratory, so red monks film. This is recorded, it's going to be there. It's respiratory, endocrine, digestive, muscular, urinary, nervous system, cardiovascular system, skeletal system, female reproductive, integumentary system, lymphatic system, male reproductive. So those are systems. An organism, an example of organism is Professor Alonga. That's an example of organism. If you're looking for another example, you think about Lidwin. All right. So we are organisms, right? And a group of organisms like us here that we are in this class now, this is a population. All right. So that's it. Let's go. If you have questions, don't forget, while we have things to cover, and I know that, like I said, this is like a review because of the things you already learned, but you can always stop to ask me questions if you have questions. That's why it's a lecture here and not that I'm giving a recorded lecture, okay? So you can always ask me questions if you have. Like I said, atoms have these three components majorly. It has the electrons, it has the nucleus, but I'll come to the nucleus. It has a neutron and the proton. These are the components of an electron, of an atom. Now, inside the nucleus is where you have neutron and proton. So in essence, a better way to write it mathematically is going to be nucleus equals neutron plus proton. So that means inside the nucleus, you have the proton. The proton is the purple proton, and the neutron is the one that looks like lilac. So inside the proton, inside the nucleus, you have the proton and the neutron, right? Proton and neutrons are inside the nucleus. So in essence, we just say the components of an atom are three. Number one, electron. Number two, neutron. Number three, proton. Whereas we know that the neutron and proton makes up the nucleus. All right. Now, out of these three, electrons have insignificant weight. So because their weight is insignificant, what actually determines the weight of an electron, of an atom, are these two guys here. So these two determines the weight of an atom, which we call atomic mass. So atomic mass in essence is equal to neutron plus proton. Electron is there, but it's insignificant because in the real sense, what is an electron? Electron just circulates around, it travels around the orbit, which I'm going to talk about a little bit. All right, let's go. So, like I said, atomic number, no, I've not said that. You know, I told you about proton right now. And so, proton number plus neutron number equals atomic mass. So you can take note, I said atomic mass, not atomic number. There's difference between mass and number. Like myself now, I am number 5 in my family, but I am not, my mass is not 5. My weight is not 5. So atomic number is different from atomic mass. Sometimes it may be the same coincidentally, but it is not a rule. The fact that I am number 2 in a place does not mean my mass number is also 2. Of course, you agree that my mass number is not 2. If you put me on a scale now and measure me, I'm not going to weigh 2. However, I could be position 2, position 1, position 3 in any place. All right? So atomic number is different from atomic mass. Don't confuse that. Now, proton number, take note of this with me, equals atomic number. So when you can, atomic number and proton number, they are the same, not mass. The way to get atomic mass is to add proton number and neutron number together. So proton number is equal to atomic number. And listen, if you are talking about neutral element, neutral, what does neutral mean? Neutral means it doesn't have charge. So a neutral element will be like chlorine, sodium. These are neutral. These are neutral. But this, look at this. Is this neutral? Is this neutral? Thank you. It is not neutral. Is this neutral?
No.
No, it has charges, so that's not neutral. So this rule I want to talk about now does not apply to this. It applies to this. So when an element is neutral, the atomic number will also be equal to the electron number. For neutral. But generally, proton number is equal to atomic number. But when it is neutral, electron number will be equal to proton number as well. But if it is not neutral, the electron number will change. I'll talk about that later if I have to. All right. So I've talked about everything here. Let's go. So this shows you a little picture of everything I was talking about. Now look at this. I'll just talk about 1 or 2 of them and I'll continue. So hydrogen, for instance, that's number 1. Atomic number is 1. Now let me ask you, is this hydrogen here, is it neutral or not neutral?
Neutral.
Thank you. It's neutral. Now, in actual sense, what is the opposite of neutral? If it is non-neutral, so look at this now. Neutral atom. I'm not rushing because I know I'm not going to finish the chapter anyway, and I don't plan to finish it. But I will make my lecture video where I discuss this available for you to catch up with it. Okay? But it's so that if you need a refresher on what you learned before, which I believe most of you learned, you can look at it. So neutral atom is sodium like this is neutral. Carbon is neutral like this. Oxygen is neutral like this. Phosphorus is neutral like this. Potassium is neutral like this. Calcium is neutral like this. These are neutral. Now, if it is not neutral, we call it ions. Now, interestingly, ions can be 2 types. It can be anion or cation. If it is anion, it means it is negative. If it is cation, it means it is positive. So this will be anion now, Cl minus. It is not neutral, it is anion. This will be cation. Does that make sense? Now, fluorine, Fl minus, will be anion as well. Ca2 plus will be cation. H plus will be cation, hydrogen here. All right, so that's the way it works. Let's go. So looking at this now, you can see hydrogen here is neutral. Atomic number is 1. If I ask you now, what will be its proton number?
1.
1, thank you. Since it's neutral, what will be its electron number?
1.
1 as well. But coincidentally, the atomic mass of hydrogen is also 1. Now, I told you, atomic mass is different from atomic number. It doesn't have to be equal, but it can be coincidentally equal. Just like there could be a time that I was 5 months and I was also 5 pounds. I'm just kidding with that. Just like that. So if it happens like that, it's coincidental. It does not mean it's a rule. So like for hydrogen, it happens that it also has a mass number of 1, but that is not a rule. Now look at this. If you look at carbon, for instance, now carbon, this is the symbol. It's number 6 on the periodic table. So its atomic number is 6 and the proton number is 6. Because it's neutral, the electron number will also be what? 6. How do we get the atomic mass? It is neutron number plus proton number. Now, carbon have atomic number of 6, and its neutron number is also 6. So 6 plus 6 will be equals 12. But we have different kind of carbons. For some of you that have done this in chemistry or in biology or A&P, carbon can have neutron that is 7. It can also have neutron that is 8. And so we call that isotopes. If you still remember now, call it isotopes. So there is a carbon that is called carbon 12. There's carbon 13 and there's carbon 14. They are all isotopes. Interestingly, they all have the same proton number of 6 because proton number does not change. It's like your W number. It doesn't change. It's like your position in the family. It doesn't change. If you are number 1, even if they give birth to 13 after you, it's still number 1. If they give birth to 30 after you, you are still number 1. And those numbers remain the same. Either you travel to UK, you travel to anywhere in the world, your number remains the same in your family. So if I'm number 5, for instance, that I'm number 5. Regardless, I'm number 5. So proton number is your identity number, like your social security. It doesn't change. But neutron can change, like you see here. This carbon now is different neutron. This carbon is different neutron. This carbon is different neutron, which is why the mass number changed. All right. So that's a nitrogen here is number 7. It also has neutron number of 7, interestingly. But look at this. Sodium is atomic number of 7, proton number of 7. So proton plus neutron. Interestingly, its neutron is number 12. And that makes its atomic mass to be 23. So sometimes you see that the neutron number may be the same, but there's no rule. Does anyone goes in and out? Oh, sorry. Is anyone having network issues logging in and out? Is that affecting anyone generally, or is just Florence? Looks like it's you alone. You are on your own on this. It may be your network also. All right, thank you. So you notice that some elements have the same atomic number and neutron number, but it's not a rule. Take note. Neutron number and electron and neutron number and proton number or atomic number has no rule that connects them that says they have to be the same. Like here now, if you look at this, you see that the neutron number here is 6, not 5. All right, and that's why this is 11, because proton plus neutron equals 11, right? So if you come here, you see that the neutron number is 6, the neutron number is 7, just like this. Here also the neutron number is 8. Here the neutron number is not 11. So you can't generalize neutron number. Neutron number is different on its own. It can be the same sometimes. It may not be the same. Nothing says it will be the same. If you come here now, you see that the neutron number here is 16. And that's why it's 31. Whereas if you come here, the neutron number is also 16 like this. So nothing, there's no rule about it being the same. All right, let me ask you a question now. Can somebody tell me what is the neutron number here for manganese? What is the neutron number? What do you think the neutron number is?
Like 29?
Thank you. That's perfect. The neutron number is 29. And that's why the atomic mass is 54. All right, let's go. I don't think we need anything too much on that already. Good. You remember I talked about isotopes the other time and I used carbon? Oh, exactly. That's the same carbon here. You see that? So this carbon here, like I told you, carbon will always be the same. So you see, proton number is the same. Proton number is the same. Proton number is the same for all the carbons. Now, neutron number, different, different, different. So neutron number is different. So what is an isotope? If you want to define it, an isotope is an element that have the same proton number or atomic number or different neutron number. That's it. So we say that atomic number is the same, but proton number is different. That is an isotope. So an isotope is an element with the same proton number, like you can see here, proton number or atomic number, proton number, the same. Neutron number, different for the same element. That is an isotope. So we say these are isotopes. The same thing, you can have isotope for hydrogen. So you have hydrogen that is hydrogen 1, hydrogen 2 also exists, hydrogen 3 exists. So in this hydrogen now, they have different mass number. All right, so usually we have isotopes for some of those elements. Let's go. Now, I'll be talking about electronic configuration and how it affects their reactions. Electronic configuration and how it affects their reaction. Like I told you, I won't finish this chapter, but I will post videos that I feel will help, and I'll also make this video available to reinforce the things that I won't cover. I can't finish it. I don't plan to finish it. I just want to do a quick refresher on a few things. All right, so let's go and talk about valence. Now, when you see valence electron, when you say valence, isotope is an element with the same number of carbon but different number of proton. No, the same number of proton, the same atomic number of proton number, but different neutron number. Example is carbon, not the same number of carbon. So isotopes are elements with the same number of atomic number or proton number, neutron number, not the same. So keys, atomic number or proton number, they are the same. All right. So the same proton number, different neutron number. But we are looking at the same element. That's why I use example of carbon being carbon 12, carbon 13, carbon 14. So we are not going to say carbon and nitrogen are isotopes. No. No. We are saying that these elements exist in different forms. There's a form that is carbon 12, which has 6 neutrons. Another form, carbon 13, it has 7 neutrons. Another form, carbon 14, it has 8 neutrons. These are isotopes, different neutron numbers. Now, what do we call valence electron? Now, there's something that valence electron is, it's interesting actually, because the valence of an electron is what determines the reaction of that element. So look at it now. See, okay, I'll talk about late coming after the class. Now, valence is what determines the reactivity of an element. So for instance, what number do we call sodium? Do you remember? What's the atomic number of sodium? Atomic number or proton number? What number is sodium? What's its atomic number or proton number?
Is it 16?
No, it's 11. The atomic number is 11. So now look at a rule with me. Look at this rule with me. Now the atomic number is 11. So when you want to write the electronic configuration of sodium, you know what the way we write it? I will show it to you and I will explain it. The simple way to write it is to say 2 8, 1. I will explain. The first 2 means that the first ring is going to have 2 electrons. Then the second 8 means that the second ring we have 8 electrons. 2, 3, 4, 5, 6, 7, 8. And the third ring has 1 electron. That is why we write it that way. Now, what does that mean? A general rule is this. First shell can only accommodate first shell of any element, not just sodium. I'm just using sodium as an example. Can only accommodate 2 electrons. That's the maximum. So even if an electron have 100, even if an element have 100 electrons, the first shell can only accommodate 2 electrons. Second shell accommodates 8 electrons. But if I ask you, does it mean it will always have 8 electrons? Do you think that every element will always have up to 8 electrons? I thought I was going to get a response. Do you think that every element we have
No.
we always have up to 8 electrons?
No.
No. I will explain. Very good. No. Then the third shell can also have up to 8 electrons. Every other shell, aside from the first shell, can have up to 8. But what happened in case of carbon, for instance? What number is carbon on the periodic table? Thank you. It's number 6. So what does that mean? It means the first shell is going to have 2 electrons. And the second shell, we have 4 electrons. Because if you, thank you, because if you put 2 in the first, you're going to have 4 left. So you're going to put 1, 2, 3, 4. Now you notice I didn't put just 2, 2 on different sides because I have to circulate it. It's a rule. The rule says that you pair, you single first, you put it in singles first before you double. All right. So that is carbon. The second shell has capacity to have 8, but in case of carbon, it doesn't have 8. In fact, the total of its electron is not to 8, so it doesn't have 8 to put in a second shell. It only has 4 to put in that second shell. All right, that is that. Now let me do this now and show you something from here. I want to clean this. If I can clean it, I hope this thing will let me do that. Okay, eraser. Don't mind me. I've been trying to get used to this thing. I'm having some connection issues. Yes, I noticed that Kelechi. I noticed you were in and out. Hopefully it will stabilize. So look at this. All right, so look at me now. For sodium, how many electrons? What is the atomic number of sodium? Can you help me now? What is the atomic number of sodium? Thank you. Sodium is number 11, right? So if it's number 11, how many electrons will be in the first shell? 2. Thank you. How many electrons will be in the second shell?
8.
Thank you. How many will be in the third?
1.
Oh, I'm sorry. We did sodium already. I was trying to do another one. Kara, I was looking at that. So let me get this off and do for chlorine. I wanted to do for chlorine. I didn't know I was doing sodium again. So let's do chlorine now. So how many electrons does chlorine have in total?
17.
What's the atomic number? 17. Thank you. So what is going to be in the first shell? How many will be there?
2.
Thank you. Second shell?
8.
Thank you. Third shell?
7.
Thank you. So now let me explain what I need to explain to you here. So in quote, the first shell is going to have, let me just use this for my electron in this case. Okay. Second shell has 1. Oops. Don't mind me. Second shell have 2, 3, 4, 5, 6, 7, 8. And third shell, we have 7. 1, 2, 3, 4, 5, 6, 7. Now, the place you put it doesn't matter as long as you have put it in order. You can put your single, you can leave this here as single. I want to leave this here as single to make it easy for me to connect it, and I'll show you what I want to do. So now look at this. This is sodium, 281. This is chlorine, 287. Which of them is stable? Which of them do you think is stable? So I know Kiera is saying that chlorine is stable. All right. Let me see more responses. Which of them is stable?
Neither.
Yeah, none of them. None of them. There's none of them that is stable. Because in the rule of electron, you are either stable or non-stable. There's nothing like this is more stable, this is less stable. It's either is stable or is unstable. So now, chlorine and sodium are not stable. And stability is what they both want to achieve. So they both will be looking for ways to become stable. And that is the reason I cannot see screen again. Oops. But can you still see my screen, every other person? Okay, so you may want to log out and log in if you can't see my screen. I think it may be from your network there. Sorry about that. Now, so chlorine will look for ways to become stable. Sodium also is looking for ways to be stable. Because they are both unstable, that's why you usually see them in chemical reaction. So it is instability that determines chemical reactivity or their ability to react. It's based on their instability. A chemical that is stable or an element that is stable will not react. The ones that are not stable react. And I will show you an example of them. So if you look at this now, this one is not stable because it needs to be full to be stable. And what fills the third shell? How many electrons fills the third shell, like I told you? How many electrons is supposed to be in the third shell if it's going to be stable? How many?
8.
It's 8. Aside from this, it's actually 8 at this level. Don't worry. If you get to chemistry, you talk about 18, 32, all of that, but you don't need that now. For the first shell, 2. Second shell, 8. Third shell, 8, 8, 8 after that. Now, for this shell to be stable, it needs to be 8 or to disappear. And I'll show you how. For chlorine, how many electrons does it need more to become stable?
1.
It needs 1 more. Now, look at these two now. if the two of them want to react, which of them do you think is comfortable for you to lose, and which of them do you think is logical to gain? All right, thank you, Kara. So it is logical that sodium lose its 1, transfer it to this place so that chlorine gain that 1. In this case now, we will say that sodium have lost an electron. Now, when sodium loses an electron, what do you think sodium will now be? Sodium will become an ion, and in fact, a cation. So sodium, when it loses an electron, it now becomes Na+. It has lost an electron, so it doesn't have 11 electrons again. It only has 10 electrons now. Does that make sense? Now, thank you. Chlorine, on the other hand, has gained an electron. Now, in this case, it's no longer regular chlorine, it's now Cl-. Do you know why it's carrying minus? Because now, instead of having 17 electrons, it now has 18. To avoid confusion, so that whenever anybody sees chlorine, they are not thinking, oh, chlorine is number 18. No, chlorine is not number 18. It's number 17, but it has 18 electrons. But the minus is there because it's just 1. We call it Cl-. If it is 2, we put Cl2-. But it's Cl- because it's just 1. And sodium is also 1. That's why we just leave it as Na+, meaning that Na+1. Now, that negative there is telling you that there is 1 that is borrowed, is on the negative. You say this 1, I borrowed it, is on the negative. And think about it as well. Electron is negative value on its own. So when you get negative value, you become more negative anyway, because what you got is negative. Right? So sodium is going to become positive for losing negative. It's just like you lost a negative value. Maybe you are somebody that procrastinated before. If you lose that procrastination is a negative value, you become positive. And if you are not somebody that procrastinated before, you now learned to procrastinate. You have learned a negative trait. So you have become more negative. So sodium lost a negative, it became positive. Chlorine gained a negative, it became negative. Exactly. So it means chlorine is owing. It's just like you got a credit card. You think you are richer when you spend the money, but you are actually in debt. You are in the negative. All right. So that is actually that. Now, in this case, what have we formed? We have formed NaCl. Now, this is how chemical reaction happen. What kind of bond is this? We call it ionic bond because it involves ions. Na+, Cl-. So it forms NaCl. So we call it ionic bond. Now, what is ionic bond? You see, is a transfer of electron from a metal to a non-metal. So metal transfer electron to a non-metal. So a metal lost an electron, a non-metal gained an electron. That is ionic bond. So you see, a metal transfer its electron to a non-metal, ionic bond. Is it okay to continue? Thank you. Thank you. So this is what I've explained there. I can just continue now. This shows you the configuration for all of them, how they arrange, all of that. Okay, now let's go. I want to see if I can. I've talked about valence. I will talk about it a little more again to explain it. I'm starting to talk about chemical bond, and I've talked about ionic bond already. Now, if we now want to talk about valence of an electron, look at this. The valence here, if you look at this one, for instance, now, the valence, you see, valence electron in an atom shell that interact with other atoms. That is what we call valence electron. Now, okay, let me come here. So I've talked about this one ionic bond. I will now go ahead and talk about covalent bond now. So I've explained ionic bond. And you see, it occurs when two atoms with vastly different electronegativity come near. What do we mean by vastly different electronegativity? It's a big word, but it doesn't mean anything too much other than one is negative, one is positive, just like what you saw now. Atoms are either positive, cation. Sodium, for instance, is the one that is cation. Chlorine is the one that is anion for what we just looked at. They came together, form a bond. The bond is called ionic bond. And example of usually an example of that is always salt. Like potassium chloride is a salt. Sodium chloride is a salt. Calcium chloride is a salt. Those are all ionic bonds. So let me ask you, is it always every bond that require that an element will lose and then the other element will gain? Do you think it's no? It's not. Some bonds require sharing. They are not losing, they are not gaining, they are using it together. So it's like partnership, it's like cooperation. Because it's like cooperation, we call it covalent. Covalent. Because they are using their valence, thank you, I'm saying the chat. They are using their valence together. So look at this now. So valence, combining capacity of an atom. Positive if the atom has electrons to give up. Negative if atom has space to fill. Stable when the outer electron shell contains 8 electrons. So look at this now. Covalent is when they are sharing. But look at this. Now, if I ask you, I will use this image to explain it and it will make sense to you. I told you covalent means sharing. Covalent simply means they are sharing electrons. Now, if you ask myself, Kara, what do you like to eat most? You better answer because I may just send some out now. What is it?
Cheeseburgers.
Cheeseburger. Very good. Where do you buy it from?
I make it myself.
Wow, that's good. So now, she likes to eat cheeseburger and she likes to make it herself. I don't like cheeseburger so much because I don't like the cheese so much. Now, if you now ask myself and Kara to eat cheeseburger, let's say Florence just say that she wants to buy something for both of us, and then Florence, okay, I'll come to that jollof too. I like that one too. Now, if Florence says she wants to buy cheeseburger for myself and Kara, and then
Lily,
who do you think we eat more? Who do you think will eat more of the burger?
put it in here. Wait
Thank
for
you.
2 hours.
Let me mute my suspect for that voice. Okay, I think I got it. Now, if myself and Kara was supposed to now eat the cheeseburger, she's going to eat more because she likes it more. Not because she wants to be unfair to me, but because she have affinity for it more. So, sharing of electrons will not always be equal. There are sometimes that electron sharing will be unequal. There are sometimes that it will be equal. So now, when we have to share that cheeseburger, she's going to eat more. So we say that it is sharing, but it is unequal sharing. So we say it is sharing, but it is unequal sharing. This kind of sharing. So we say we are sharing, but it's unequal sharing. When sharing is unequal in chemical biology, we call it polar. Because it's still sharing, we call it polar covalent bond, meaning that the sharing is not equal. Now, why do we call it polar? Because a lot more of the cheeseburger goes to her side than to my side. She's going to have more than what I'm going to have. So it's becoming polar. Polar meaning that it's going to a pole more than my pole. It's drawing to one pole, is not centralized. That's why the polar comes in. So polar covalent bond. So this is the kind of bond that you see in water, for instance. You see, let's say this is water now on the screen. This is hydrogen. This is another hydrogen. Of course, you know water is H2O, whereas this is oxygen. So when they are sharing electron, oxygen likes electron more, even though they are sharing. I will explain to you. Oxygen have electrons more. So you see, how many electrons? Look at this ring. How many electrons do you see on this ring that I'm tracing? How many electrons are there? 2. You see, this electron 1, electron 2. There are 2 electrons on this ring. Now, on this other ring, how many electrons is there? It's also 2. So, whereas, how many electrons does I thought that the polar meant white or now? I'm not sure if I get your question. Can you hear me?
Yes.
Okay. Let me see if I will get your question well, but follow me a little bit. Now, I'm talking about 2.
It means I've understand that term properly now, because I've always thought it means either white or snow
That makes sense.
for polar bear. So that's how I associated it with. But now I understand it better.
It makes more sense now, right?
Yes.
Thank you. I'm happy for that. So look at this now. This is hydrogen. Now let me ask you, how many electrons does hydrogen have normally? Normal hydrogen. How many electrons does it have normally? When it's neutral, is 1. Thank you, Stephanie. Now, that 1, is it stable? No. Because how many electrons will make the first shell stable?
2.
2. So whereas hydrogen only have 1. So hydrogen is looking for stability. Now think about this with me. How many electrons is in oxygen? Oxygen is number 8. So the first shell will be 2. And the second shell will be 6. So you see the first shell is 2, complete. The third shell is 6. The second shell is 6. So it's not stable. It's also looking for stability. So you see it's going to be looking for stability. So for it to have stability, it's going to share with 1 hydrogen and another 1 hydrogen. So if you share 1 electron with this, it will become 7. Share another electron with this, it then becomes 8. And so the hydrogen associated with the carbon up to the oxygen will also become stable. So that's what you see here. So this oxygen, this electron here is for this hydrogen. This electron here is for this hydrogen. So this is sharing with this oxygen. This is also sharing with this oxygen, such that if you look at this oxygen now, look at this. Look at what I'm tracing. How many electrons can you count on this circle that I trace now? You can see it there. So if you look at this oxygen, it now looks stable. If you also look at this hydrogen by itself, it also has 2. So in quotes, this guy have 2, this guy have 8, this guy have 2. Now, do they actually have 12? They don't have 12 in total. They actually have 8 in total, but they shared it together. Now, when they shared it together, every one of them appeared stable, even though they attained the stability by sharing. Now, why do we say this is not equal sharing? I will show you something now, but it will make sense to you when I show you the equal sharing. This is unequal sharing. Why? Again, oxygen is here, and oxygen loves electron more than hydrogen, just like Kara likes cheeseburger more than myself. So oxygen is going to draw electron to itself more. Ideally, it should be like this. This should be the shape. Look at it. I'm saying ideally, but this is not. This should be the shape ideally, if it were to be equal sharing. But in this case, it's not equal sharing. The shape is always like this. Look at what the shape is always like. What does this shape mean? This shape means that hydrogen and oxygen are not sharing something on the same level. Oxygen is pulling everything to itself. The hydrogen does not have a stand because oxygen is pulling everything to itself. That is the difference between this is the correct and this, which is wrong. So I will go ahead and show you the equal sharing now. Why do I say it's unequal sharing? Because we say that oxygen is an electronegative element. It loves electron. So now let me show you equal sharing now. I'm going back to show you equal sharing. Again, polar, unequal. That is the key word there. Unequal sharing of electrons due to different electronegativity. Which one have highest electronegativity? Oxygen in this case. Now look at this. Look at this. Equal sharing. Look at equal sharing now. You see how the two of them stayed side by side. You see how they stayed side by side. And not that oxygen is here and hydrogen cannot stay side by side. Hydrogen is like this. This is unequal sharing. Someone is drawing more to its side. But this is equal sharing. You see both of them on the same side. If we have done this also with carbon and oxygen now, for instance, you see, they will be like this because it's equal sharing. So you see, hydrogen and hydrogen, they share with themselves equally. Both of them are hydrogen, so they like electron the same way. So this is H2 now, hydrogen gas. It is equal sharing. So this is non-polar. We call this equal sharing, non-polar covalent bond. All right? Like this is oxygen and oxygen forming O2, equal sharing. So you see non-polar shared electron spend equal amount. You see that? Equal amount of time around each nucleus. Nobody is stealing more. Nobody. It's just like Florence mentioned jollof rice the other time. Let's say we like jollof rice the same way together. Jollof rice is a kind of rice that is jollof. That's the best way to define it. It's a Nigerian food, actually. All right. Now, my daughter called it red rice. So if you are eating red rice now, and both of us are eating it, I don't know who will eat more than the other, because perhaps both of us may like it. All right. Or maybe myself and Lisa is eating mashed potato, and let's say both of us like it. Both of us are eating it at the same level. Nobody is sharing on equal. All right. So that is electrons. That is bond. I've explained polar covalent bond. Polar means it is unequal sharing. Non-polar, which is the example that you are seeing on the screen, it is equal sharing. These are non-polar, equal sharing. And then I've explained polar, which is unequal, that leaves hydrogen to be swept off its feet when sharing with oxygen, because it can't just maintain stability. It maintains stability, it doesn't have the same affinity for electron like oxygen does. So oxygen is pulling it, even though they are sharing. All right, so I've talked about ionic bond. That's ionic bond. I've talked about that. Hydrogen bond is a kind of affinity. That's what you see between water molecules. All right, so normal water molecule. Let me see. I should have an image of that here. Very good. Let me see. I will show you one. I will try to make one if I can't find. Okay, good. So like this now, you see, look at this. This is water molecule. This is water molecule. This is water molecule. This is water molecule. You notice that water always look like it's not different molecules. It always look like it's together, even though water is mysterious. You know, it's not sticky like oil, but then it still looks like it's packed together. That's the same reason when you go to the swimming pool and you jump into the water doesn't let you touch the floor of the pool. The water is still on the surface and it looks like this water has a tension on the surface, like a pressure that will not let you get in. That is called surface tension. How do we get the surface tension? It is formed by this hydrogen bond that holds water molecule together. So this is an hydrogen bond. This is an hydrogen bond, hydrogen bond, hydrogen bond. If I ask you, what is the bond in between this hydrogen and oxygen in the water molecule? What is that bond called? Inside a water molecule. Don't confuse it. What is the name of this bond here that holds hydrogen and oxygen together in a water molecule? In a water molecule. What is that bond called? People, are you confused? Okay, good. That's polar covalent bond. Thank you. Polar covalent bond is the bond that holds the element of a water molecule together. But if you want to connect a water molecule to another water molecule, what's the name of the bond?
Hydrogen bond.
Very good. It is that hydrogen bond that makes it impossible for you to just enter into a swimming pool and then you are touching the floor of the swimming pool. Has that ever happened to you that you jump into a swimming pool, but you are touching the floor straight? Is that possible? Do you mean it has happened that you dive into a swimming pool like this and your body is touching the floor straight? That's not possible. Very good. Yeah. So what holds the water molecule together is a hydrogen bond. It's a force of attraction. All right. So that's the hydrogen bond there. That's the same bond that makes it look like the water molecules are always together. And we call that cohesion. That if you go to a swimming pool now, I use this very funny example. I know we have to be running off now, but if you go to a swimming pool, this is the last thing I'll talk about. You go to a swimming pool. So the tendency of water molecules to be together is called cohesion. All right. But there's another property which we call adhesion. This is the last thing I'm talking about, then I'll round up. You get to a swimming pool and you notice that the water is not touching the wall of the pool. Are you going to jump into that pool? I'm sure you won't jump in. You would think like maybe it's a setup because you don't expect water to be disconnected from the surface. The property that makes water to always be connected to the surface is what we call adhesion. It's also because of the hydrogen bond. All right, so I'm going to stop here. Like I said, this is like a review chapter, so I'm going to post the video that I have for this chapter, not directly for this, for Bio 1 or AP1, where I talk about this same content. I'll post that available just like a refresher for you, okay? All right, so I'll stop here so that I can take